Initially, bending a piece of metal feels final. Twist it, crumple it, and you expect it to stay deformed. After all, that's how plasticity works, right? Once atoms in a metal slide past one another under stress, they don't just slide back. But what if the metal did recover? What if, after being tightly wound or crushed, it snapped back to its original shape, almost as if it remembered how it used to be? This is the fascinating behavior of shape memory alloys, SMAs, and it lies at the heart of the shape memory alloy paradox. How can a solid metal undergo what looks like permanent deformation and then spontaneously return to its original form, apparently defying the rules of traditional materials science? Let's imagine the scene. A wire made of an SMA like nickel titanium nitinol is tightly coiled. You heat it gently with a hairdryer or warm water, and suddenly, before your eyes, it uncoils itself, perfectly returning to its original straight form. There's no internal motor, no embedded electronics, just metal atoms rearranging themselves. This isn't magic, it's physics, but it's physics that challenges our everyday intuition about how materials behave. To understand this paradox, we need to look beneath the surface, at the crystalline structure of these special alloys. Unlike ordinary metals that permanently deform when plastically strained, SMAs work through a solid state phase transformation between two different crystal structures. The austenite phase. At higher temperatures, the alloy exists in the austenite phase, a more symmetric, stable structure. When cooled or mechanically stressed, the material transitions into martensite, a more easily deformed phase composed of twinned crystal variants. Here's the key. When you bend or twist the martensitic phase, you're not forcing atoms to slip irreversibly over one another, as in plastic deformation. Instead, you're simply rearranging variants of the martensic crystal structure, which is a reversible distortion, not a permanent one. Now, when the deformed martensite is reheated, it transforms back into austenite, the internal structure realigns, and the alloy returns to its original, remembered shape without any mechanical input. This is known as the shape memory effect. But it gets even stranger. Some SMAs also exhibit super elasticity. At a constant temperature, they can be stretched significantly and will return to their original shape immediately upon release. This doesn't require heating. What's happening here is a stress-induced transformation to martensite, followed by spontaneous reversal back to austenite once the stress is removed. It feels rubbery, but it's metal. So where's the paradox? From the viewpoint of classical plasticity, metals are not supposed to reverse deformation this way. Once atoms move past their neighbors under stress, dislocations form and accumulate, locking in the shape. But SMAs bypass this entirely, not by preventing deformation, but by doing it through a different mechanism altogether. A reversible crystallographic shift, not dislocation slip. To the observer, it seems like magic. To the materials scientist, it's a masterclass in phase transitions. You might ask, how does a material remember its original shape? The memory isn't stored like data on a chip. It's encoded in the crystal lattice of the high-temperature phase. The alloy always wants to return to the lowest energy austenite form, and when the conditions are right, typically heat, it transforms back. The atoms follow an energetically favored path that reestablishes the original geometry. And this isn't just a laboratory curiosity. Shape memory alloys are used in medical stents and guide wires which expand at body temperature, eyeglass frames that snap back after being bent, actuators in robotics and aerospace that move without motors, seismic dampers in buildings and bridges. But their use also comes with challenges: fatigue from repeated cycling, precise control over transformation temperatures, and limited strain ranges compared to polymers. Nonetheless, researchers are developing new SMA compositions, including high-temperature alloys, magnetic SMA systems that push the boundaries of smart materials. Perhaps the most fascinating aspect is what this teaches us about memory and matter. SMAs blur the line between passive materials and active devices. They exhibit behavior that feels almost biological. They react, adapt, and reset without sensors or logic circuits. And they do so by leveraging a subtle, elegant feature of solid-state physics, that atomic patterns can encode a kind of physical history, a blueprint that the material reverts to time and again. So, the shape memory alloy paradox reminds us that not all deformation is permanent, and not all materials are as rigid as they seem. In the right conditions, metal can remember, move, and even heal, not in defiance of physics, but in celebration of its hidden possibilities. Shape memory alloys are extraordinary materials that appear to remember their original form. After being deformed, even bent or twisted beyond what traditional materials could recover from, they can return to their pre-deformed shape upon heating or unloading. The paradox lies in how these metals defy typical plastic deformation rules. Where normal alloys would suffer permanent dislocation-based changes, SMAs undergo reversible phase transformations instead. Their apparent memory raises fundamental questions about the nature of deformation, reversibility, and material intelligence. A bent nitinol nickel titanium wire straightens itself when heated above a specific temperature, returning to its original geometry as if the deformation had never occurred. It's like crumpling a paper flower that, instead of tearing or wrinkling, magically unfolds back to its pristine form when warmed by sunlight. The shape memory effect is based on a solid-to-solid phase transformation between two crystal structures: austenite, high temperature, symmetric phase, and martensite, low temperature, distorted phase. Deformation occurs in the martensitic phase through twinning, not dislocation movement, allowing atoms to rearrange without creating permanent defects. When heated, the martensite transforms back to austenite, and the material reverts to its original shape, effectively encoding shape as a thermally recoverable state. In biomedical stents made of nitinol, the device is compressed and inserted in its martensitic state, then expands back to its programmed shape inside the body when it warms to body temperature. It's like freezing a folded origami into a shape that unfolds itself perfectly when warmed without any external force. The core mechanism behind this behavior is diffusionless martensitic transformation, where atoms collectively shift positions to form a different crystal lattice without breaking atomic bonds. The transformation is fully reversible and occurs over a narrow temperature window. During deformation, the martensitic variants reorient rather than slip, enabling large strains, (6%), that are recovered upon reheating. The absence of dislocations and the cooperative movement of atoms are key to this reversibility paradox. In actuator applications, SMAs undergo thousands of thermal cycles, transforming repeatedly between shapes, thanks to their robust martensitic transformation pathways. It's like flipping a Rubik's Cube from one solved color arrangement to another without scrambling the pieces. You are changing configuration, not damaging structure. Shape memory behavior exemplifies adaptive complexity in materials. Global functions like remembering shape emerge from cooperative atomic transformations. These materials operate on principles similar to biological systems, storing, recalling, and adapting shape without electronics or software. SMAs challenge classical views of elasticity and plasticity, functioning more like programmable matter, where the response to stimuli is built into the material structure itself. In aerospace, SMAs are embedded in morphing wing surfaces that adjust their geometry based on air temperature and pressure, improving aerodynamic efficiency. It's like having muscles built into a plane. Each part adjusts itself like living tissue without motors or gears. The energy landscape of SMAs is dominated by thermomechanical coupling. Mechanical work is absorbed through twinning in martensite, and heat input triggers reverse transformation into austenite. This coupling allows SMAs to convert thermal energy into mechanical work and vice versa, acting as both sensors and actuators. Hysteresis exists in the transformation cycle, reflecting energy dissipation, but the overall loop is remarkably reversible. An SMA spring lifts a weight when heated by electric current, converting thermal input into motion with no external control system. It's like winding a toy with heat instead of a key. The energy input triggers a dance, choreographed at the atomic level. SMAs store memory not in software or DNA, but in the metastable arrangement of atoms. The original shape is a low-energy configuration of the austenite phase, and the martensitic variants temporarily encode deformation. This reversible encoding and decoding of geometric information aligns with information theory principles, where order and retrievability are maintained despite transient disorder. The system locally forgets but globally remembers. After multiple deformation cycles, the SMA still returns to its trained shape because the transformation path is encoded in the lattice geometry, not disrupted by defects. It's like a song imprinted into a music box's cylinder. You can twist and shake the box, but once the crank turns again, the melody plays back exactly as before. SMAs are key enablers of soft robotics, self-healing structures, and minimally invasive devices. Their compact, quiet, and wire-like nature makes them ideal for environments where space, simplicity, or biocompatibility matter. As materials that combine actuation, sensing, and intelligence, they support the development of distributed, autonomous systems that respond to environmental changes without requiring embedded electronics. NASA has deployed SMA-based mechanisms in satellites for passive deployment of antennae and solar panels, where traditional motors are bulky and prone to failure. It's like giving your satellite a built-in muscle that flexes only when it feels the warmth of sunlight. Despite their elegance, SMAs face challenges. Repeated cycling can lead to fatigue cracks, especially in harsh environments. Their slow response time, limited strain range, and narrow temperature window also limit use in fast, high-power applications. Controlling shape recovery and transformation temperature with precision requires material engineering at both the microstructure and alloy composition levels. Medical implants must be carefully engineered so that the transformation temperature is close to body temperature, avoiding premature actuation or thermal instability. It's like designing a key that opens a door only when it's warm, but the metal must not melt, corrode, or warp after many uses. Future research is exploring multi-phase alloys, nanoparticle reinforced SMAs, and hybrid systems that couple shape memory with magnetism, electricity, or light. At the nanoscale, SMAs could be used for molecular actuators, artificial muscles, and responsive surfaces. Emerging materials may exhibit dual memory effects, programmable transformations, or bio-inspired learning behaviors. SMAs blur the line between structure and function, offering a model for smart, adaptive math. Scientists are developing light-activated SMAs that change shape with a laser beam, offering precise remote actuation without wires. It's like training metal to dance to a song you play from a distance. The shape is not imposed by force, but by orchestrated atomic choreography,